Welcome to the complete generative AI roadmap for 2026. Whether you're a software developer, data analyst, or complete beginner, this video will guide you through everything you need to learn to become a Gen AI expert. Generative AI is the most transformative technology of our time. From ChatGPT to Stable Diffusion, from AI agents to autonomous coding assistants, understanding Gen AI opens doors to incredible career opportunities. In this video, we'll cover the complete learning path. Python and math foundations, machine learning, deep learning, NLP, transformers, generative techniques, prompt engineering, fine-tuning, AI agents, and deployment. Let's get started. Every Gen AI journey starts with solid foundations. Python is the universal language of AI. You need to be comfortable with core syntax, object-oriented programming, list comprehensions, decorators, and generators. Mathematics is equally important. Linear algebra gives you vectors, matrices, and eigenvalues, which are the backbone of neural networks. Every layer in a neural network is essentially a matrix multiplication. Calculus, specifically derivatives and the chain rule, is how models learn through backpropagation. Probability and statistics help you understand distributions, Bayes' theorem, and how models make predictions under uncertainty. For libraries, master NumPy for numerical computing, Pandas for data manipulation, and Matplotlib for visualization. Jupyter Notebooks will be your daily workspace for experimentation. Don't try to learn all the math first. Learn it alongside your ML journey. When you encounter a concept like gradient descent, that's when calculus becomes real and meaningful. Machine learning is the foundation that generative AI is built upon. There are three main paradigms you need to understand. Supervised learning uses labeled data to learn a mapping from inputs to outputs. Classification predicts categories like spam or not spam. Regression predicts continuous values like house prices. Key algorithms include linear regression, logistic regression, decision trees, and random forest. Unsupervised learning finds hidden patterns in data without labels. Clustering groups similar data points together using algorithms like k-means. Dimensionality reduction with PCA helps visualize high-dimensional data. Reinforcement learning trains an agent to make decisions by rewarding good actions and penalizing bad ones. This is how ChatGPT was fine-tuned using RLHF, reinforcement learning from human feedback. Model evaluation is critical. Learn accuracy, precision, recall, F1 score, and AUC. Use cross-validation to ensure your model generalizes. Scikit-learn is your go-to library for classical ML. The key insight, ML is about learning patterns from data. Gen AI takes this further by learning to generate new data that follows those same patterns. Deep learning is where AI gets its power. Neural networks with multiple layers can learn incredibly complex patterns that traditional ML cannot. A neural network has neurons organized in layers. Each neuron computes a weighted sum of inputs, adds a bias, and applies an activation function like ReLU or sigmoid. The network learns by adjusting these weights. Backpropagation is how networks learn. It computes the gradient of the loss function with respect to each weight using the chain rule from calculus. Then gradient descent updates the weights to minimize the error. Convolutional neural networks or CNNs are designed for images. They use convolution layers to detect features like edges and textures, and pooling layers to reduce dimensionality. CNNs power image recognition, object detection, and computer vision. Recurrent neural networks or RNNs process sequential data like text and audio. LSTMs and GRUs solve the vanishing gradient problem, allowing the network to remember long-range dependencies. For frameworks, PyTorch is the research favorite with its dynamic computation graphs. TensorFlow and Keras are popular for production deployment. Learn PyTorch first as most Gen AI research uses it. Natural language processing is how machines understand human language. This is directly foundational to LLMs and Gen AI. Tokenization splits text into units the model can process. Word-level tokenization is simple but can't handle unknown words. Subword tokenization like byte pair encoding or BPE breaks words into common pieces. This is what GPT and most modern models use. Word embeddings represent words as dense vectors in a continuous space. Word2Vec showed that you can capture meaning, where king minus man plus woman equals queen. Glove and fast text improved on this idea. The sequence-to-sequence architecture with encoder and decoder networks enabled machine translation, text summarization, and question answering. The encoder reads the input and the decoder generates the output. The attention mechanism was the game changer. Instead of compressing all input into a single vector, attention lets the decoder look at all encoder states and focus on the most relevant parts. This single idea led directly to the transformer architecture. Understanding these NLP concepts is essential because transformers and LLMs are built directly on top of tokenization, embeddings, and attention. The transformer architecture is the heart of modern Gen AI. Introduced in the famous Attention Is All You Need paper in 2017, it revolutionized everything. Self-attention is the core mechanism. Every token in the sequence computes attention scores with every other token. This captures relationships regardless of distance. A word at position 1 can directly attend to a word at position 1000. Multi-head attention runs multiple attention computations in parallel, each learning different types of relationships. One head might learn syntax, another semantics, another coreference. Positional encoding injects position information since transformers process all tokens in parallel with no inherent sense of order. Without it, the model couldn't distinguish between the dog bit the man and the man bit the dog. BERT uses the encoder for understanding. It reads text bidirectionally and excels at classification, question answering, and named entity recognition. GPT uses the decoder for generation. It predicts the next token autoregressively, which is how ChatGPT works. The key LLMs you should know are GPT-4 and Claude for commercial applications, Llama and Mistral for open source, T5 for text-to-text tasks. Understanding these architectures is what separates a Gen AI practitioner from a casual user. Now let's explore the different generative AI techniques beyond text. Each approach creates different types of content. Diffusion models are behind the image generation revolution. They work by slowly adding noise to an image until it's pure static, then learning to reverse that process. Stable Diffusion, DALL-E 3, and Midjourney all use this approach. GANs or generative adversarial networks use two competing networks. A generator creates fake images and a discriminator tries to detect them. They push each other to improve, resulting in incredibly realistic outputs. Variational autoencoders encode data into a compact latent space and then decode it back. By sampling from the latent space, you can generate new data. They're used in image generation and drug discovery. For audio, text-to-speech models like VITS and BART can generate natural-sounding speech. Music generation models can create original compositions from text descriptions. Video generation is the frontier. Models like Sora can generate realistic video from text prompts. This combines image generation, temporal consistency, and physics understanding. Multimodal AI models like GPT-4v, Claude, and LLVA can understand both images and text together, enabling visual question answering and image reasoning. Prompt engineering is the art of communicating effectively with LLMs. It's the fastest skill to learn with the highest immediate impact. Zero-shot prompting is asking the model directly without examples. Few-shot prompting provides 2 to 3 examples to guide the format and style. This simple technique can dramatically improve results. Chain-of-thought prompting asks the model to think step by step. This improves reasoning accuracy on math, logic, and complex problems by 40 to 70%. Just adding "let's think step by step" to your prompt makes a huge difference. RAG stands for Retrieval Augmented Generation. Instead of relying only on the LLM's training data, you retrieve relevant documents from your own data and include them in the prompt. This reduces hallucinations and adds real-time knowledge. The RAG pipeline works like this. First, embed your documents into vectors. Store them in a vector database like Pinecone, ChromaDB, or Weaviate. When a user asks a question, embed the query, search for similar documents, then pass them as context to the LLM. Vector databases are the backbone of RAG. They store embeddings and perform similarity search using cosine similarity or dot product. This enables semantic search where meaning matters more than exact keywords. Fine-tuning lets you customize pre-trained models for your specific use case. This is how companies build specialized AI products. Full fine-tuning updates all model parameters. It's thorough but expensive, requiring significant GPU memory and compute. For a 7 billion parameter model, you might need 4 to 8 high-end GPUs. LoRa and QLoRa are game changers. Low-rank adaptation freezes the base model and trains only small adapter matrices. This reduces trainable parameters by 90% and memory usage dramatically. You can fine-tune a 7B model on a single GPU. PFT or parameter-efficient fine-tuning includes techniques like prefix tuning, adapter layers, and prompt tuning. These methods achieve near full fine-tuning performance at a fraction of the cost. RLHF, reinforcement learning from human feedback, is how ChatGPT was aligned with human preferences. Human raters rank model outputs. A reward model learns these preferences. Then the LLM is fine-tuned using PPO to maximize the reward. DPO or direct preference optimization is a simpler alternative that doesn't need a separate reward model. It directly optimizes the model on preference pairs, making alignment much more accessible. Tools like Hugging Face Transformers, Unsloth for fast LoRa, and weights and biases for experiment tracking make fine-tuning accessible to individual developers. AI agents are the next frontier of Gen AI. Instead of just generating text, agents can reason, plan, and take actions in the real world. An AI agent combines an LLM as the brain with tools, memory, and planning capabilities. When you ask it to book a flight, it can search flights, compare prices, fill forms, and make the booking autonomously. Function calling or tool use allows LLMs to invoke external functions. The model decides which tool to use, generates the arguments, and the system executes it. This extends AI beyond text into APIs, databases, code execution, and web browsing. Memory systems give agents context across interactions. Short-term memory is the conversation history. Long-term memory uses a vector database to recall past interactions. Episodic memory remembers specific experiences. Planning strategies determine how agents tackle complex tasks. React alternates between reasoning and acting. Plan and execute creates a plan first, then execute steps. Tree of thought explores multiple reasoning paths. Popular frameworks include LangChain for building LLM applications, LlamaIndex for data-augmented agents, Crew AI for multi-agent teams, and Claude's Model Context Protocol or MCP for tool integration. Multi-agent systems use multiple specialized agents collaborating on complex tasks. One agent might research, another writes code, and a third reviews it. This is how tools like Claude Code and Cursor work internally. MLOps is how you take AI from a Jupyter notebook to a production system serving millions of users. This is where engineering meets AI. Model-serving frameworks like VLLM, text generation inference, and Llama handle the complexity of running LLMs efficiently. They implement batching, copy cache optimization, and continuous batching for high throughput. Build APIs with FastAPI for your AI models. Implement streaming responses for real-time token-by-token output. Use WebSockets for interactive applications. Add rate limiting and authentication for production use. Quantization shrinks model size dramatically. GGUF, GPTQ, and AWQ can reduce a model from 16-bit to 4-bit precision, cutting memory by 75% with minimal quality loss. This lets you run large models on consumer hardware. Cloud deployment options include AWS SageMaker, Azure ML, GCP Vertex AI, and Hugging Face inference endpoints. Choose based on your scale, budget, and existing cloud infrastructure. Monitoring is essential. Track latency, token usage, cost per query, error rates, and output quality. Detect model drift and hallucinations. Tools like Langsmith, weights and biases, and Prometheus help you observe your AI in production. Congratulations! You now have the complete roadmap for mastering generative AI. Let's recap your learning path. Start with Python and math foundations. Build up through machine learning, deep learning, and NLP. Master transformers and LLMs, the heart of Gen AI. Then specialize in prompt engineering, RAG, fine-tuning, and AI agents. Finally, learn to deploy and serve models in production. The best way to learn is by building. Start a project today. Build a RAG chatbot, fine-tune a model on your data, or create an AI agent. The tools are free and accessible. If this video helped you, please like and subscribe for more AI content. Your Gen AI journey starts now.